Welcome back, everybody. AP Chemistry. This is Unit 6, Section 2, taking a look at the colligative properties of solutions and something called von Hoff factors. Colligative properties are things that basically, if you add something to a solution, it's going to affect those properties of the solution itself. And that is a function of the number of particles that you're going to be adding to them. It's not really affecting or a factor of the chemistry going on in there, but really what the effect of those particles are in the solution. So if we take a look at an equation like this, it's a pretty simple one actually. We're going to see, take for example, the boiling point of water. We know that to be around 100 degrees Celsius. But if I add some particles in here, and by adding particles, I mean if I change the molality of the solution by adding, say, salt to it, what's going to happen is it's going to actually raise up that boiling point of water. It's going to be hotter when it's actually boiling. So this K value is just going to be a value that's going to be provided for us. It's a constant. And here is a function of the particles, and I'll talk about the von Hoff in a moment when we apply it, okay? Same thing is going to happen to a freezing point. It's actually going to bring that down, so we refer to this as a freezing point depression. It brings down the freezing point of water, and this will be bringing up the boiling point of water. So we'll take a look at those in action, but the math is going to be the same. Those constants are going to be provided in a table, and I've handed out those, and you'll also see a listing of what values different solutions are going to freeze at or boil at, or solvents, I should say, are going to freeze and boil at any given conditions. So you don't have to worry about those factors, and we can actually just plug things in to some simple examples of this. We're going to be actually taking a look at water, and we're going to boil it and freeze it by adding some sugar to it, some sucrose. All right, they give you the mass of the sucrose is going to be 343 grams. And be careful, we're going to add it to 100 grams of solution, not solvent, okay? Now, the reason that's important is because if I take a look at my equation, the change in freezing point, we'll start with that one, is going to be a function of this constant of 1.86. And now I have to find that molality, don't I? Well, to find the molality of sucrose, I have 2 grams of sucrose, and it already gives me 343. Now the sheet that I've got, I use 342, so I'll use that, but just your number is going to be off just a little bit with this, and that's okay. That ends up being 0.00585 moles of sucrose. And here's where the trick comes in. I have 100 grams of solution. I don't have 100 grams of solvent. Remember, in your solution, you've got two things. You've got 2 grams of your sucrose, and it must have been 98 grams of water. Now remember, I needed to know that because the next step right here is molality. And so I needed to divide my 0.00585 moles of sucrose by 0.098 kilograms of water. And so if I calculate out that molality, I end up with a 0.0597 molal solution. So that's what I put right here, 0.0597. Now, I'm using sucrose, which is molecular. When I put that into solution, it doesn't dissociate into ions. It just stays as that compound. So its multiplying factor, or von Hoff factor, is going to be a 1. So if I do this calculation real quick, I end up with a value of 0.11 degrees Celsius. Now, water normally freezes at 0 degrees Celsius. This will bring it down. So now it's going to freeze at a negative 0.11 degrees Celsius. Let's take a look at how it affects the boiling point. Now my boiling point constant is going to be a 0.51. My molality I've already calculated for a 0.0597. And again, it's molecular, so it just acts as one particle. So my change in boiling point, it ends up being 0.030 degrees Celsius. Now, water typically boils at 100, and so now it's going to be boiling at 100.030 degrees Celsius. Okay, so that's pretty simple. You just take a look at those types of examples and ask that question. Now, what does it look like when I include my von Hoff factor if I have an ionic compound? All right, an example of an ionic compound, it just has a metal in there, and so I'd have sodium chloride. So sodium chloride, that will dissociate into the sodium ion and the chloride ion. And notice it's a 1-to-1 ratio there, so that will act as 2 particles. Okay, once again, I have 100 grams of solution here, and so I had 2 grams of salt and 98 grams of water. Okay, So obviously, I'm going to do the boiling and freezing point. Let's take a look at my freezing point again. And my freezing point constant is going to be a 1.86. I need to find my molality. So 2 grams of sodium chloride is 58.5 grams per mole. And so I end up with, in this case, 0.0342 moles of sodium chloride. And remember, I have only 98 grams of water, so that's a 0.098 kilograms. And I have then a molality of 0.0349. All right, so 0.0349 goes here. Now, it acts as 2 particles, remember. So I have 2 particles interacting with that. And now if you do your calculation, I'm going to end up being a 1.30. Now, what does that mean? That means that I'm going to have a freezing point of negative 1.30. Remember, in the previous problem, it was 0.11. So it's a big difference. If I take a look at my boiling point now, let's see how the salt will affect that. So that's going to be the 0.51 times a 0.0349. That's my molality. And again, there's 2 particles. And so my change is going to end up being a 0.36. So now my value, my water is going to boil at 100.36 degrees Celsius. Okay, so it did raise that boiling point just a little bit by having 2 particles in there. So you can see how the von Hoff factor is going to be affecting the different solutions. All right, we can now do a different permutation on this. And I can use some observed identities or observed properties to figure out the molar mass of some different solutions. Okay, so number 9, we're going to be taking a look, and we're going to dissolve something into solution. And you'll notice this looks a little bit different because they refer to this as a non-volatile solute. What that means, it doesn't dissociate into ions, it acts as 1 particle. All right, so I can go through and I see that it is in water, and it is grams of water, so I don't have to do that other game. That ends up being a 0.150 kilograms. Okay. Now, water does typically boil at 100. So notice that my change is a 0.34 degrees Celsius. Okay, it changed by that much. So I know that value. All right, so that will equal, the boiling point constant is a 0.51. I don't know my molality. That's actually what I'm trying to find. I want to find the molar mass of this thing, which is a function of grams per mole. Okay, but molality, remember, is moles per kilogram of solvent. Okay, so we're going to piece those pieces together. Now, my von Hoff factor is going to be a 1 because it's non-volatile. Okay, so the first step is to solve for my molality. My molality ends up being 0.667 moles of solute. Now remember, that molality is per 1 kilogram of water, isn't it? But I don't have 1 kilogram of water. I have 0.150 kilograms. So if I multiply that by 0.150, notice the kilograms of water are gone. I end up with a value of 0.10 moles of solute. Okay, almost done because I was given 18 grams. What is molar mass? Molar mass is grams per mole. So if I just take 18.0 grams over 0.1 moles, I end up with a value of 180 grams per mole. And I gave you a little hint here. It is actually glucose in there, and that's the formula mass for glucose. So it's working this problem in reverse, trying to find molality, and then you convert that into molar mass. Let's do another one with a different solution, and this particular one is ethylene glycol. Okay, and so in the problem, we're going to be taking a look. I have 10 liters of water. 1 liter is 1 kilogram, so this is exactly 10 kilograms of water. And I have my molar mass here. Let's see, and the question is asking what mass of this is going to be allowing us to not freeze until negative 23.3. All right, so that means that my change in freezing is at 23.3 degrees Celsius. Remember, that's the change. And so that's going to be a function of 1.86 times my molality, because I want to know what mass. So that's going to be a function of my molality. And notice that this ethylene glycol is molecular, so it acts as one particle. It's non-volatile. All right, so that's my number of ions. So my molality is going to be 12.5 moles. And that's going to be in 1 kilogram of water. That's molality. But I don't have 1 kilogram. I have 10 kilograms. And so what do I end up with? I end up with 125 moles of ethylene glycol. Okay? Now, what does that mean? Well, if I have 125 moles, because I'm trying to find what mass of ethylene glycol, it gives me that I have 1 mole is 62.1 grams. I end up with 7,762.5 grams. Okay, that's how much it would take to actually get it to freeze at a negative 23.3. Okay, now we're going to do one last problem with these, and then we'll move on to osmotic pressure. A chemist is trying to take a look at this, and the reason we're looking for this is trying to find, again, a molar mass. And so we've done this type of problem before, and so we're trying to figure out what's going on here. Remember, molar mass is grams per mole. Okay, we can use this to identify maybe what the hormone might be or whatever. So you notice that the freezing point depression was determined to be a 0.240. Okay, so that's my change, 0.240 degrees Celsius. That's going to be a function, but remember, it's the value is always going to be a little bit different. We've been working with water the entire time, and so I've got this problem in here is we've got it in benzene. So if I just look up the constant for benzene, the freezing point constant for benzene was a 5.12. Okay, again, that's just a value we look at. We want to find my molality, and we do know that because it's a hormone and all there, it's going to be molecular. It's going to have a multiplier of 1. So my molality ends up being 0.0469 moles per 1 kilogram of benzene. But I don't have a kilogram of benzene, do I? I have 15 grams. So that ends up being a 0.015 kilograms. And so my number of moles ends up being 0.0007035 moles of the compound. Okay? How many grams did I have in here? Well, I had 0.546 grams. So if I take that, 0.546 grams, I end up with a value of 780 grams per mole. Okay, so that was, what was that, 0.546. Okay, so 700 grams per mole, and we can identify it from there. Cool, so that's the different permutations we can use, even with different solutions in there, rather than just pure water. You can just use those things as we go. There's one other thing I want to show you guys with this particular section, and that's something dealing with osmotic pressure. Okay, osmotic pressure, it's, again, just an equation that we work with. It's taking a look. What osmosis is if we have this tube and we put some kind of barrier in between, something that's permeable, and I have pure water on this side. Okay, this is a concept in biology class as well, and I have solutes on the inside on this way. The particles, this barrier is so that the particles can't diffuse this way. So what's going to happen is my water molecules are going to diffuse across the membrane in that direction. Okay, so that's what's going on in here, and we can measure that pressure in atmospheres of pressure. We can measure that as a function of the von Hoff factor, as a function of molarity now. We have a constant, and then my T is always going to be in Kelvin. Okay, so let's take a look at some examples, just 2 quick examples of how do we calculate those things and what that would be. And let's take a look at an example in like an anatomy class or a medical where we have to figure out if the red blood cell is going to be able to survive. All right, so we want to know the pressure of this particular problem, and I have to pull it apart a little bit because my von Hoff factor, I have 2 particles here. Okay, my molarity of solution. All right, so I need to figure out, I have this much water, and I have this many grams of sodium chloride. So let's convert my 0.0029 grams of sodium chloride, 58.5 grams to 1 mole. And so that ends up being, this is a ridiculously small number, 0.123449572 moles of sodium chloride. Okay, that's in 1 liter of solution. Okay, but I don't have a liter of solution. I have 0.0250 milliliters. Remember, that needs to be in liters. Okay, so it's a 0.000049572 divided by 0.1231250 liters of solution. Okay, and so what that ends up being is, let's see, lost my spot here. That ends up being a 1.98 moles of solution. Whew, that's a lot of work just to find 1.98 molar solution. Now, I've got my Von Hoff, I've got my molarity, then I just plug in my 0.08306 and my temperature, because things will move at different temperatures. Remember how to find Kelvin. Kelvin equals 273 plus my 25 degrees Celsius. And so my Kelvin in this case ends up being 298. And so 298 here, I end up with my osmotic pressure being a value of 96.9 atmospheres. Now, the problem was saying the cell will burst if it goes anything over. So guess what? There goes that cell. So we got it too strong, and that cell will burst. Okay, that's how we work with that particular example. Let's do one more, and this is dealing with a protein. And we know that we have 0.001 grams of it, and it's dissolved in enough water to make 1 milliliter of solution. Okay, the pressure was found to be 1.12 torrs, and so notice this is torrs, and we need to be in atmospheres. So here's my conversion from torrs to atmospheres. 1.12 torr, and my conversion from torrs to atmospheres is 760 torrs to 1 atmosphere. Okay, that ends up being 0.00147 atmospheres. Okay, so let's plug in our values. 0.00147 atmospheres equals, it's a protein, so it's non-volatile. My Von Hoff is 1. Let's see, my molarity is what we're solving for. Okay. Okay, we want to find the molar mass. Remember, that's grams per mole. So we got to plug that in. My 0.08206 is my constant, and my temperature is 298 again. So my molarity ends up being 0.000060 moles of the protein per 1 liter of solution. But I don't have a liter, do I? I have exactly 1 milliliter. So 1 milliliter is 0.001 liters. And so I end up with 6.01 times 10 to the negative 8 moles of my protein. Okay, so how many grams did I have? Because remember, molar mass is grams per mole. We're going to see this all year long, guys. When we see that question, molar mass, we have to think grams per mole. Well, I was given 0.001 grams. For every 6.01 times 10 to the negative 8, that means that I'm going to need 16,639 grams of this protein per mole. That's my molar mass. Okay? And we are done. So these problems, just know the equation, keep your head about you, get all those factors in there. You should be able to do problems 1 through 7, and then we'll be in lab doing a freezing point depression lab. So that's going to be pretty cool. All right, you guys take care, and good luck.